Yeah, so thanks everyone. Welcome to the first workshop and challenge on computer vision in the built environments for the design, construction, and operation of buildings. This workshop is organized by a group of researchers from ETH Zurich, Oregon State University, Georgia Tech, and Stanford University. The reason we are having this workshop is that recently, in the recent years, 3D vision, especially work that starts from point clouds, have received significant interest in computer vision. For example, two of the most famous papers, PointNet and PointNet++, published in 2017, has already been cited to get more than 2,000 times. And this is a pretty new interest from the computer vision side. But 3D point clouds has always been a very crucial data input format in the AEC community, which is the community of architecture and construction, in design and construction. So the computer vision community has got this paradigm of working with a lot of data and using deep learning and then build powerful algorithms to solve those learning problems. But the AEC community has a significant amount of research problems that are super important. They are realistic for all the buildings, to the entire built environment, which include all the buildings and other things that are built. And there are a significant amount of research problems that have a very high practical impact. So in this workshop, we aim to bring the two communities together so that we can further research in both areas. Today, we have 4 invited talks in the workshop where we would like to have a balance on people from the computer vision community and the AEC community. So the first, the talks would be delivered by Dr. Derek Hoym from UIUC and Dr. Yasu Furukawa from Simon Fraser University. Those are computer vision community researchers that have developed a significant amount of research on the problem in buildings or the built environment. And on the other side, we have Dr. Frederick Bosche from University of Edinburgh, and then Dr. Eleni Papadonikolaki from University College London, who are from the AEC community. They will also talk about their work utilizing computer vision in their work. And besides the invited talks, we will also have show the results of the first scan to beam challenge. We'll also show the results of the first scan to beam challenge, which we hosted in the past 3 months. And the goal of the challenge is to try to get a convergent approach to solve the problems in computer vision and AEC community. So this challenge is supported by the National Science Foundation Convergence Accelerator Program, and we especially try to put people together from both computer vision and the AEC and civil engineering and also other disciplines together, so to build this challenge. So our challenge starts from 3D point clouds, and then we have 2 tasks. The first task is 2D floor plan reconstruction, and then the second task is 3D model reconstruction. So before talking about the challenge itself, let me just make a brief overview of the previous data sets in computer vision about buildings. So there are 3 data sets that are very important in terms of semantic and instance segmentation in computer vision, and they are ScanNet, S3DIS, and Semantic 3D. So those 3 data sets usually work on segmentation of elements, including building elements such as walls, doors, and windows, as well as furniture in the building. And then in Semantic 3D, we focus on the 3D recognition of the outside facade of the buildings. And also we have 3D scene graph data set. So this data set cares about a lot of building elements, as well as the attributes of those building elements, as well as their relationships. it's a very well-built data set, but those annotations are very hard to come by. So this data set is built in simulation, but it's like very high definition simulations, very well done. And then there is also previous scan to beam buildings. Previous scan to beam data sets. This was mostly from the AEC community. One can see that previously there was Ochman et al. That has 6 floors. This is from Denmark. And then Malik et al. That has 5 buildings with multiple floors. And then another one, which is kind of published in ICCV in 2019, has 100 floors, and it converts RGBD scans into this vector graphics floor plan. But the main problem with this latter data set is that there's only a few rooms per building, and then there is no structural components such as doors, and then it was not evaluated topologically, as well as no wall thickness over there. So in our data set, we obtained this data from the state of Oregon from 3 public buildings in the state of Oregon. It was scanned with the BLK 360 scanner. And then this data set includes a total of 91 floors of point clouds. We separated them into 2D tasks and 3D tasks. And then in 2D tasks, there was a training and validation and testing, and then 3D tasks as well. So in the 2D task, the training and validation point clouds and the corresponding 2D floor plans are released to the contestants. And in the case of testing, only the point clouds were released, and then contestants submit their results on an evaluation server that we built. So our data has complicated layouts with multiple different floor types, including office, garage, and storage space. So as some of the examples you can see here, each floor has many rooms, because this is like an office scenario. So there's many rooms, different kind of separators, and different kind of facilities, including labs, garage, parking lots, and things like that, as well as realistic noise. So you can see that different from simulation data, our scanner captures noise sometimes, for example, outside the window. So like even if you are scanning inside the window, if the window is open, you can capture some points that are outside of the window, which kind of is also interesting as a realistic data set.
Right.
And then in terms of the ground truths, what we obtained from the state of Oregon is 2D ground truths, wireframe CAD models. So those are as built CAD models. So they are curated to reflect the built environment. It is mostly aligned with point clouds, but it's actually in a different coordinate system. So we had to do our alignment to kind of correct the coordinate system to the point cloud. Besides, the CAD models come in DWG file format, and it is difficult for open source software to directly access those data. So we had to do our own work to convert it to an open source format to make available. So I would like to credit the team that developed all the codes and then the models and then the evaluation servers for the challenge. So this team is a very interdisciplinary team from Oregon State University, Stony Brook University, as well as a company O-Vision. So there's a total of 11 people that directly participated in the development of the challenge. And then this is really joint work with a lot of people and quite a lot of work to get this data ready. So let's look briefly at the data cleanup process. There's quite a few different issues from both the point cloud side and the CAD model side. So one can see that, one can see that our point clouds are really big. So they are kind of architectural standards. So you can see our original point clouds for each building, they have like 267 different scans. And then this is like for one building. And then there's like 681 million points in that building. So after the cleanup process, we've cleaned it up, combined it all together, put everything in the same coordinate system, and then it becomes one file with 120 million points. One can note that the scale here is significantly higher than a lot of the point cloud data sets people have worked before in computer vision. There are a lot of different issues such as data corruption because of the large size of the data, as well as missing ceiling and floors, as well as some user errors in certain point clouds. So we spent a lot of time cleaning it up, merging the scans, downsampling to 1 centimeter point spacing. And then there's a lot of automated scripts and programs written, as well as anonymizing the data and removing location information. In terms of the CAD model, as we mentioned, the CAD data were in different coordinate systems at the later scan, so we had to align them. And we actually used a combination of two alignment registration algorithms to align the CAD models together with the point clouds. Besides, as mentioned, we extracted the CAD models out of the DWG format and then just retained some of the building elements that we are evaluating, and then we kind of change it into an open source format so that everybody can access it from Python easily. In terms of the metrics, we would like to build metrics that are realistic and useful to the AEC community. So there has been this process where people from 3 different areas are talking together each week, and then we over a process of quite a few months to develop the metrics, and then we covered point metrics, area metrics, and topological metrics. We have involved the people from Stony Brook who are very familiar with medical imaging, where they evaluate a lot of topological metrics in order to develop those quantitative topological metrics for the challenge. So let's start with the point metrics. In terms of 2D evaluation, we got this point metrics that are just simple matching. So basically, every contestant would provide endpoints for the walls and the doors, those building elements. And then there are ground truth endpoints. Those are matched with the Hungarian algorithm. And then and then only points that are close enough are considered a match. So here we choose 3 different radiuses, which are 2 centimeters, 5 centimeters, and 10 centimeters. One thing that is well worth noting is that in computer vision, we usually have kind of loose matching criteria. For example, we like to say, okay, if we can match within 10 centimeters, that's already great. However, this is far short from the requirements in the AEC community. So they would even like to match up to only like a 1 centimeter difference, which we cannot do at this moment because our data that we released is downsampled to 1 centimeter. So if you actually want that 1 centimeter level accuracy, you need to process even larger point clouds. So here, this is like one of the difference that is unveiled during the challenge development process between the communities, that in the AEC community, people like to be very precise. And as a computer vision person, I'm just starting to realize that is the case. And we also have room metrics. This is kind of similar to segmentation metrics that we usually use in computer vision. It's intersection over union, where we compute the quotient between the area of overlap over the area of union between the predicted room and the ground truth room. So here we only measure, in this case, in this year, we are only measuring this on rooms, and then in the future, would like to measure it with more building elements. Here, any openings that are less than 40 centimeter wide were ignored because they could just be walls. So that's what we used. And then in terms of topological errors, we developed 2 metrics. so those are pretty new to the evaluation of point clouds. We believe it's one of the novel things in our challenge. The first metric is called warping error. So here the warping error is a metric that penalizes topological disagreement. So in order to explain it, we have to, I'll get questions about this at the end of the presentation. So in order to explain this, so one can see there is ground truth, and then there is ground truth image here, and then there is image A and image B. And then for image B, it is, in terms of overlap, it doesn't overlap perfectly with the ground truth. However, one can remove one pixel at a time from this image B, so that if you remove one pixel at a time from this red block, and finally you will get to exactly the same to the ground truth. In terms of topology, B is kind of the same with the ground truth. So it actually does not have any warping error. So when computing the warping error, we will just remove one pixel at a time from B, and then we will remove like all these pixels on the boundary, one pixel at a time, so that this removal will not change the topology of this segmentation B. So once we hit the ground truth, that'll be great, and then we will see that B does not have any warping error. So in terms of this A cannot be warped to the ground truth in a topological, in a manner that does not change topology. So which means in layman terms, does not introduce or remove any holes from the image or from the segmentation actually. So in this case, after doing all the warping that removed all the topologically correct errors, we would be left with the topologically incorrect errors. And finally, we normalize this warping error metric. Oh, by the way, at any time for anybody who like to ask questions, you can also put in the question and answer, there's a Q&A, which everybody can post anything in there at any time. And then we will have the speakers to answer those questions at the end of the presentation. Yeah, so this is one of the topological metrics we are having. And then the next topological metric we developed was called Betti error. And here we are looking at the number of connected components within a certain, within a randomly chosen patch in the image. So here we are just looking at the topology of rooms. And for example, we could be just putting a square patch looking like this. And then we will check how many connected components are in that patch. So like say 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, and so on. And then we'll check like in the same patch in the ground truth, what's the difference between the number of connected components as in the contestants provided to the CAD models or to the floor plans. So then we will check the difference on this number, and then we will average over many randomly sampled patches. So I think in our case, we average over 2,000 randomly sampled patches. And then finally, we present the challenge results. So in the 2D challenge, we have 5 participants from all over the world. In China and United States, Hong Kong, Germany, as well as Turkey. And then the winner, the winner submission had, came from Institute of Automation and Chinese Academy of Sciences, who obtained the best IOU score as well as the best precision. But we can also see that there are some other people who have obtained better recall as well as better topological metrics. So we really hope to develop this set of metrics so that we can evaluate everybody from multiple different facets. So in this workshop, the top 2, so the winner and the runner-up of the challenge will be presenting their results or their approaches. And then in the 3D challenge, because we spent a lot of time cleaning up the data, we didn't really get enough time to provide enough 3D ground truth models for automatic evaluation. Hence, we decided to employ a panel of organizers to manually check the 3D models. So each submission was reviewed by 4 different panel members on their accuracy, completeness, and correctness. And then a small bonus score was added for entries that provided solid models and IFC format. So in terms of this 3D evaluation, we just had qualitative metrics such as accuracy, which expresses how close the model is to the reference, completeness that expresses the proportion of the reference that overlaps with the model, as well as correctness, which expresses to what extent the elements in the model are present in the reference. And in terms of solid models, so we gave bonuses for models that actually put walls as a solid wall rather than as 2 different lines, right? So if you just do 2 different lines and then there's nothing in the middle, this is not the most correct 3D model. So we gave bonuses to those solid models, as well as if you kind of add, if you export it into IFC format, which is a standard format and very important in the AEC community. So the 3D challenge results are presented here, which included 4 submissions. The submission from Purdue University that is super point graphs and augmented synthetic real point clouds won the challenge by scoring the highest in all of the 3 metrics: accuracy, completeness, and correctness, as well as obtaining a total score of 2494. And then so both them and then the second place approach, Point Weaver from Technical University of Munich, would give a presentation today. So that's all I would like to introduce about the workshop and the challenge. So now I would like to give you an overview of the schedule for the rest of the workshop. So here the time zone is set to Central Daylight Time, which is GMT -5. You could convert it to your own time zone. So right after this will be the invited talk from Professor Derek Hoym. And then we would have the second place and the winner from the 2D challenge floor plan reconstruction to present their methodology. And then we'll have another keynote talk from Dr. Eleni Papadoni-Kolaki. And then we'll have a 15 minutes short break. And then 2 more presentations from the challenge from the 3D building model reconstruction from TU Munich and then Purdue University. And then 2 more invited talks. And then at 4:45 Central Time, we will have a panel discussion, which will be moderated by Dr. Marzia Bopani. So we'll talk about interesting questions in between that would try to combine the AEC and the computer vision community. And finally, we'll have closing remarks and topics for the next workshop. How to communicate with us? So there is this Zoom webinar Q&A interface, which all the attendees can access. So you can always send your questions through the Q&A interface. You can either post anonymously or use your own name to post it. This workshop is recorded, and then the recording will be publicly available after some editing. So that would probably take a little while after the workshop. And then you can also post the questions that you would like the panel to talk about. So, and then we can also take a look at that. Yeah, so we will answer your logistic related questions in the interface, and feel free to post in social media using CVPR 2021 CV for AEC.